Now, what's the difference between AC and DC? What does it mean? How does he sing like that? And why are they in schoolboy uniforms? All those first two questions and more today when we're talking about AC and DC. AC stands for alternating current, or wisselspanning in Dutch, and DC stands for direct current, or gelijkspanning in Dutch. When I was doing research at the University of, we don't really call it university in Dutch, which makes me a little bit mad, I actually had a course of 10 weeks, which was called wisselspanning. So there was 10 weeks of just learning about alternating current. It's really interesting, and I really loved the subject. Thank you, Professor Van Dalen. It was amazing. I also got a really good grade for it after 2 tries. Let's figure out what these types of current mean, shall we? Because actually, it's mostly the voltage that we're working with. In my case, I don't really know why we're calling them currents, because we're usually talking about the voltages. It's kind of the same thing, but this is what it would look like in a graph if you put both of the types in one graph. So I put DC as green, just a straight line, and AC as a wibbly sine wave in red. Batteries make a direct current. They do this by freeing up electrons on their negative side and absorbing electrons on the positive side. And, well, they make space at the positive side, so all the electrons that are bunched up at the negative side will want to go to the positive side. So if you give them some kind of material to flow through, like a wire, copper wire, they will move from negative to positive. That's just what they're going to do. That's how batteries work, and that's relatively simple. That's how we've been doing it in these past episodes. And now, alternating current is made quite differently, and it's using magnets, and that's kind of a problem because magnets are kind of confusing. Magnets, how do they work? Haha, funny meme. But I'm gonna try to explain it. Magnets have this field around them called a magnetic field. You cannot see it, but you can definitely see the effects of it when you're using magnets. They have they work at a distance. It's creepy action at a distance is what they call that. Not really. That's what I call it. That's a different thing. But, they work at a distance, which is interesting. So they have this field around them. And this field actually affects electrons in conducting material as well, because you can think of electrons as very tiny little magnets that get affected by this magnetic field. So if you have a wire, let's say my arm, and you pass a magnet over it, it has a changing magnetic field. The magnetic field is changing in the wire as well. And all these electrons feel this changing magnetic field, and they kind of get tugged along with the magnet. So if I'm pulling the magnet this way, all these electrons also kind of get tugged that way, just a tiny bit, because it's a very, very weak magnetic force on the electrons there, but they get tugged along just a tiny bit. And if I do this, they get tugged along the other way. And the harder I do that, the faster I get the magnetic field to move, the harder they get tugged. So if I get something, a very big magnet that moves like that, I can get these electrons to kind of just move like that as well. And because they're all in this big wire, this material, they bump against each other, so it's not just near the magnet where the current starts flowing, these electrons start moving all in the same direction, but because they're bumping against each other in a huge row of electrons, the whole wire, the entire system that is connected to that little part where the magnet is moving, will actually get a current going through them. You can think of it as a bunch of billiard balls just spanning the entire length of the wire, And if one of these billiard balls gets moved, it will bump against all the others, and all the other billiards will also move. It's not really how it works. It kind of is how it works. It's an old wives' tale that electrons are like billiard balls. It's kind of wrong, but it sort of works. So we get just a big magnet, and it moves all these electrons by making this changing magnetic field. So a power plant is just a big hunk of a big hunk of a magnet that is spinning, because that's easier to do, but it's still a changing magnetic field. And it's spinning, and around that is all that wire, and all these electrons in that wire get tugged by the spinning of the magnet. How do you make it spin? Well, with a big steam engine. You make something hot with either solar energy or nuclear energy or whatever. You make it hot and it starts creating steam, and that steam pushes something, and then the magnet turns, and then you get electricity. That's how electricity is made. But because it's the spinning thing, it goes left and right. These magnets have to go left and right. And so you get this thing. The electrons go to the right, and the electrons go to the left, and the electrons go to the right, and the electrons go to the left. So there was a question a while ago at Ohm's law where I asked, what is negative voltage? Well, what negative voltage means is the electrons are just going the opposite direction. That's all it means. I hope you figured that out by now, or you heard it from me somehow. And that's how AC current is made. Let me just check my script again. Things of note, things that you should remember, are things like, well, a battery is always direct current, always gelijkspanning, always DC. It cannot create an alternating current. That's not how batteries work. They work with chemicals. They don't work with magnets, and they make DC. Wall outlets, anything that has a big amount of power from a wall, is AC, because it's made by big power plants. Anything that's coming from a power plant will be AC. Anything that's moving that you can hear that makes electricity is also AC, because DC is chemical reactions. You can't really see that. It's not moving. And AC works with spinning magnets, so that's moving. So anything that's moving will create AC. So that includes generators, usually. Unless it's a big old battery generator, but maybe that's something for the future. I don't know. And you can take one of the two types and turn it into the other, but that's a lot of finagling with circuitry, and it's kind of weird, and you don't really want to get into that too much. And lastly, signals. Many signals, like audio signal, analog audio signal, is alternating currents. And the frequency is the information in there, and the voltage is the strength of the signal. So how loud, in the case of sound, how loud the sound is. So you can do some really interesting stuff with AC, because apparently you can send information over this frequency. Really cool stuff. It is AC where things get really interesting, especially for the audio people here. We're going to get a little bit into light as well. And lots of components just react much more interestingly on AC than on DC. So we're going to talk about capacitors pretty soon. And as always,
while I am a licensed physics teacher, this does not make me an expert on the subject. I'm wrong sometimes. Sometimes I know I am, but simplify my explanation at the expense of being completely correct. Sometimes I actually don't know. In either case, I've got a pretty good grasp on the laws of nature and how things work. For the purposes of these videos, the exact correct descriptions of phenomena is not important. I'm trying to give students a new way to look at this world with a technical and logical view. Please feel free to contact me to discuss any of the subject matter within video.